Hello, welcome to this afternoon's presentation on BMP sizing, looking behind the sizing tools and understanding a little bit of the science and the theory behind the proprietary stormwater separator systems in particular, but I'll touch on a few other things as well. My name is Philip Taylor. I'm Hydro International's product specialist for America's stormwater. I've been with Hydro for about 13 years now, and in the more recent times, I've spent a lot of time looking at sizing tools and developing sizing tools for engineers and for our sales reps to use and promote our products. As part of it, I've learned a lot about the sizing and the theory and the science and the math behind it, and I wanted to share some of those experiences with you because I think it will help understand a little bit about what goes into basically behind this equipment. Even though it's often simple equipment, there is a lot of work that goes into developing this equipment and developing the sizing tools that are used with it. If I can just get this to work, here we go. After the presentation, there will be a short survey. Anyone that takes the survey will be in the draw for a $50 Amazon gift card, and also the PDH certificates will be emailed out no later than tomorrow, which is the 31st. We had over 300 people register for this webinar, so I'd like to really thank people for doing that. It's really good to get that sort of support and that attendance. I think we have close to 180 to 190 people online at the moment. The presentation is being recorded and it will be available through Hydro's YouTube channel. I've also PDF'd this presentation, so any of the hyperlinks that are in it you can get, and you can download that from the handout section of this webinar. So if you just click the handouts, you'll be able to get a PDF copy of this presentation. So we're just going to talk a little bit about Hydro. I'm going to run through 3 polls. I just want to get a feel for how people use this equipment and what results they get. So 3 short polls, and then basically the rest of the presentation goes into sizing and related stuff. I didn't want to break it into too many sections. It's all related, and I just wanted to run through it. Should take about 30, 35, maybe 40 minutes. So Hydro International as a company has been around for over 30 years. In fact, the origin of the company goes back into the early 1960s with the development of the original vortex flow control valve. We developed separators in the early, I believe, 80s, and have sold thousands of separators worldwide. We have 2 hydraulics labs. We have one in Portland, Maine, and one in the UK, and these allow us to do a lot of research and a lot of testing. In fact, the hydraulics lab we have in Portland, Maine is a world-class lab. We do work in over 33 countries, so we see a lot of stuff from around the world, a lot of different situations, a lot of different technologies. We have over 200 employees situated around the world. We have a wet weather wastewater division in the in the US, situated in the West Coast and near Hillsborough. Our stormwater division is in Portland, Maine. The company is headquartered in the UK, and so we have representative offices in both the United Arab Emirates and in Australia. Our primary areas of business are stormwater, wastewater, and combined sewers. And a lot of the products are related and overlap. A lot of the technology is similar. We do collaborative research with universities and other research organizations. And of course, this industry really lives on a lot of certification and pre-approvals. And that is one of the reasons we have a hydraulics lab. This is a time-consuming part of our business. It takes a lot of energy, a lot of effort. We spend a tremendous amount of time doing testing and research. Within the stormwater division, we have separators, screens, filters, bioinfiltration systems, as well as vortex flow control valves. So we have a good cross-section of products that can address many of the stormwater issues. So I'm going to try and start poll 1 here and start getting some information. So let me launch this poll. So they're fairly simple. We're just getting an idea of just how often you might use these stormwater separators or proprietary systems. And I'll just keep this open for just a few more seconds here. I think we have most of the answers in, so I'll just close this poll. And share the results here. And we see a fairly even split between sort of the frequently, infrequently, occasionally. So it's a fairly even split about how often people use these. I think that's sort of what we find when we do these sort of surveys, that a majority of people sort of use them once or twice a year, maybe 3 or 4 times, and a few consultants use them 10 to 15 times a year. So I'm going to switch to a second poll now. And if you're using these products, how are you sizing these products? Let me just get the next poll here. So if you've used products like proprietary systems, do you size it yourself? Do you tend to just go to some tables, either from the vendor or from the local regulatory agency? Do you call the vendors, or do you use an online tool? So what's the kind of the most common way that you do this? Okay, I think we're getting most of the answers in now. Okay, so let's close this poll and share the answers with you. Now, most of you will call vendors, or you'll do it yourself, or use printed tables. Let's see. So printed tables are fairly simple. Calling the vendors is also really simple. It transfers a lot of the work to the vendor, and that's what we're here for, so we don't mind that. We do that every day. So you've got a result, you've done the design, and let's say you put it out the bid, or you go and ask for some pricing, and you put it out on the street, basically. So the third poll I'm going to look at, I just want to get some idea if you got alternates, or someone proposed something different. How did that sort of compare, if it was like for like, whether they sized smaller, or that you were surprised by the difference between what it was that you sized up and what it was that you got back at the end of the day? Okay, we're just about there. All right, I'll close the poll on this one now, share that with you. And the vast majority of people, I think, are pretty happy. Things came in about where they planned, and a small percentage size larger, and a smaller percentage size smaller. So this comes down to, let me just skip through a couple of slides here. The sizing tools, we make many sizing tools, and the reason we do this is that A, because we have many products, and also B, there's no standard in the industry on how things are sized or how things are approved. So we have many tools. We have sizing curves, we have sizing tables, we have Excel spreadsheets, and we have online apps. So we have all these tools, and this is just a small cross-section. The last count for our stormwater products, I believe I was up to about a dozen different sizing tools. And some of these are very specific, like for instance, the city of Lévis in Quebec has a very specific format that they want the sizing done on, and a table presented on the sizing. And so we have a special tool for that. So if you have a need for a sizing tool, a special spreadsheet, that's something we can produce for you as part of our services. So there's a lot of questions that come in when it comes to sizing. Usually we get a call from an engineer, a designer working on a project, and it's fairly vague sometimes. They just need to get a separator, or they need something to retreat 80% TSS. And usually this just starts a whole lot of questions going. So what are you treating for? Is it TSS? And is there a definition to that particle size? Is it nutrients? Is it trash? Are you interested in oil? Because each one of these questions leads you down a different path of maybe which piece of equipment is better or more suited to the situation and the application. It's not always clear when you look online at the vendor's website what's the best piece of equipment to use. And so sometimes it's better just to call someone and have a chat and see what they're talking about and try and work out exactly what's required for that site. And things like how much do you need to remove? You know, is it 80%? Is it 80% TSS and 90% of annual rainfall treatment? Is it an effluent limit? All these things are different. They're going to create different results, and it might also influence how things are sized and what sizing equations are used or what sizing method is used. And on the regulation side, we see many different regulations in stormwater manuals, and more current stormwater manuals are really starting to catch up with us a little bit and updating their stormwater treatment side to be more prescriptive and more defined as to what they want and how they want it done. And these are all typically what we see in manuals currently. It's 80% TSS, 90% TSS based on a NERP curve with 60% total phosphorus removal. Match the pre-development total phosphorus and total nitrogen runoff concentrations. No more than 30 milligrams per litre effluent limit. 80% based on OK 110. If we're out in the West Coast in California, they have a regulation saying you've got to remove 100% of trash greater than 5 millimeters. So we have all these different regulations that we deal with on a day-to-day basis, and it's really hard to get one tool to do all that. So each one requires a special design process. And when we're looking at this, we also are dealing with not just the equipment, but with the rain, the runoff rate. It's often, especially when dealing with filters, the runoff volume and longevity and service life come into it. With the pollutant, it's things like what's the gradation of the particle sizes coming in? Is it large? Is it small? Are the concentrations big? Are the concentrations small? Nutrients, whether you're going for particulate or dissolved nutrients, trash, hydrocarbons, etc. So all these things have to be matched up, and then it's a matter of matching the equipment with the pollutants, and then matching the sort of the flow rate as well with the right size of equipment. So the type of equipment and the size of equipment. When we're dealing with very coarse sand, these particle sizes, sort of 1 millimeter and greater, usually a baffle box and screening systems work pretty well. When we start working down towards the very fine sand, it's around about 100 microns and larger. That's where hydrodynamic separators work pretty well, vortex separators. As we move down to the medium silts, we're starting to really push the limits of where vortex separators can go, and then we start to look at larger ponds or filter systems. And once you drop into this sort of fine silt range and lower, you're really looking at bioinfiltration, infiltration systems, and advanced filter systems. So we're talking runoff, really. Runoff is what's transporting all the material. If you're dealing with, I live in Wisconsin, and if you're dealing with the type of runoff that we had in the last couple of weeks, you would just throw your arms up and give up. In some areas, last couple of weeks, they've had in excess of 20 inches of rain in one storm in particular. You might have seen on the news, some areas got 16 inches of rain in one afternoon. So fair bit of runoff. Now, when dealing with the pollutants in that runoff, I believe Caltrans here did some studies, and I think this comes from a study around about 2005. The first flush theory comes in. Just behind this on the graph, there is a hydrograph, and it's a real hydrograph for this test site. And there's a load of pollutants that come down with the storm. So as the storm builds up, the runoff rate increases, and the pollutant load comes with that on the front of the storm to a point where the pollutants basically are flushed out or flushed off the site, and then the water clarifies, and as the storm sort of tapers off, flow rate drops down, the water becomes clearer and cleaner. So this is the first flush theory on the front end, and that's the stuff we want to concentrate on treating. This on the back end, it's a lot more volume, it's harder to treat. So let's just look at that first flush side of things. This is often tried to be defined in many stormwater manuals, and we see it does change a lot with area to area. Now, I know many people work in their specific area and they know their specific regulation. We deal worldwide basically, and we see different regulations, but what I find is that the regulations start at around about either a 0.5 inch runoff depth or a 0.5 inch rainfall depth. There's a little bit of difference between the two, but generally that's what I find is the minimum requirement we see in many areas. And if someone was to ask me, I've got no regulation, I want to do something, then I would start by looking at this and say, well, let's look at your ½ inch runoff depth and consider that as a first flush. Going less than that is probably going to miss a lot of stuff. And now this is single event type sizing, so we're just looking at the runoff from a single event or a single storm. Peak runoff from about 1.1 inches, peak runoff from 0.6 inches per hour. These are all different regulations. On the West Coast, things tend to be a little bit more like the ½ inch rainfall, or when we get to the East Coast and you get much greater storms, or you go further south, you might end up dealing with a 2 inch rainfall depth or something like that to treat as a typical storm. Now, there's a second way of doing calculations. You don't have to look at a single stormwater event. You can look at a net annual basis or a long-term historic rainfall. And I'll go into more of this later, but that just runs basically a long-term rainfall record through a simple spreadsheet type calculation, and it kind of mimics more of a volume treatment rather than an individual storm. So when we look at the rainfall record, and this is typical in Minnesota. I've grabbed this from the Minnesota PCA's website. If you take a historic rainfall record for a site, in this case it's the St. Paul International Airport, and you look at the buildup of water over depth over a long period, we find that there's that ½ inch rainfall depth. Counts for about 60% of the total, or I should say 60% of all storms would be less than that. Probably around about 6% of the total rainfall is less than 0.5 inches. If we go up to the 90% of the total rainfall volume, then we're kind of looking at all storms less than, say, about 1.1 inches. So we've got to move things up to about 1.1 inches of rainfall depth. And if you're looking at treating a 1 year, 24-hour storm, which doesn't seem that big, it jumps up to almost a 2.5 inch rainfall depth, which is a lot more water. So the type of regulation, how much water you have to treat, really does influence how big that piece of equipment needs to be. Now, some manuals have moved forward far enough that they define a particle size distribution of what PSS is or what they're trying to treat, and that will have a tremendous impact on the type of equipment that you choose. If we are looking at removing material, say with an average particle, sorry, a medium particle size, this D50 of less than 10 micron, which we see here in Wisconsin where I live, you really have to use filters, or you got to use ponds or some other system that really can treat very, very fine material. In Minnesota, they use the Midwest NERP curve, and that moves the D50 up to around about 30, 35 microns. Still in the filter range. Typically, we see regulations written around removing of something around D50 of around 100, 110 microns, and that's usually pre-treatment or standalone treatment for coarser sediments, parking lot runoff, that sort of thing. And that's easier to deal with when you get around 100 microns. That's where the separators sort of work and live. But the distribution can be very important. If the distribution has a lot of fine material in it, like this is the New Jersey distribution, to get 80% removal, you've got to basically take out everything that's over about 30 microns to get that 80% removal. And again, you're starting to really push into the filtration territory. So the particle size distribution will have a significant impact on the type of equipment that you're dealing with and you need for your site. Now, stormwater is pretty indiscriminate. It'll lump everything together. It doesn't look at your stormwater plan and go, okay, you're trying to treat for sediments, so I'll just wash the coarse sediments off. That doesn't happen. Stormwater, when it rains, it washes off whatever's on that site, mixes it all up, and makes a real good soup of it. So you see leaf material, you see trash, you see hydrocarbons, sediments, everything comes in. So you kind of need, in some cases, you might need to do a treatment train to really address the site correctly and to get the water quality results that you need. So developing tools requires data. You just can't invent stuff. As easy as that sounds, you just can't do it. You've got to have some data. People are very good at asking questions. Regulators are becoming far more educated now and becoming much more savvy as to looking at the data. And we have different sources of data. We have the lab data done out the back with guys in white coats and clipboards. We have field data that's done out in the field with guys with white coat, clipboards, and gumboots. And we have model data, which is done with guys sitting at computers and glasses and white coats and their mouse trying to work out things through mathematical modeling. And then we have to go out there. Really, everything needs to be third-party verified. We want independents to look at the independent peer review. As I say, we have no national standards, so we tend to lean towards people like New Jersey DEP, the New Jersey Corporation for Advanced Technology, the NJCAT, Washington DOE. There are a couple of other places, Canadian ETV, and places like City of Indianapolis, which maintain a table of equipment and approvals that can be used to help benchmark and verify claims. Just because data is not verified doesn't mean it's not good data. It may not be bad data. It could be that you've collected data and it doesn't qualify strictly to the protocols of the agency you want to submit it to, so you have to put it aside. But the data itself could be well collected and good data. So unverified data has a place as well. So let's look at the lab data side when we're developing tools and trying to work out how this equipment works and how well it works. There has been a change over the last few years. The two main regulatory authorities that we would submit to, one was New Jersey through the NJCAT and the TARP protocols, and that's on the East Coast. On the West Coast, we have Washington DOE. with the tape protocols. Both used to be a lab-based, field-verified process. Now, New Jersey have gone purely to lab-based data and doing a lab-based protocol. And there are advantages to doing that because it makes the variables controllable. You can change one thing and measure the result. And you can do it fairly rapidly under a cost-controlled environment, and it's repeatable. Some of the disadvantages of this, though, is that lab conditions don't often truly mimic site conditions in terms of chemistry, temperature, particle size, distribution. There's a lot of random things that can happen on a site that a lab takes out of the equation. The good thing about a lab is that you can do a lot of benchmarking, and I'll go into a little bit of that later on. But you actually get some really good feel for how a piece of equipment should perform, because you're going to need this data in order to do field tests. But when you do lab testing, you usually end up with something like this. You end up with a graph or something, and you've got different flow rates that you've tested your equipment with, and you've measured a removal result for that flow rate. And you can plot it on a chart, and you can develop a best fit curve. You can interpolate between the points for intermediate data, and you can extrapolate high and low to extend beyond the data and get some reasonable view of the performance of the device for that particle size or for that distribution under these flow rates. And that gives you an idea of where you should be with this equipment. And you can take it to the field. Now, field data, you've got to start somewhere. So we tend to start in the lab because we want to get some idea of how big a piece of equipment should be to treat a site, because you just can't go out to a site and say, okay, I've got a site here, it's a certain size. I'm just going to guess at how big the equipment would be and put it out there, test it, and if it doesn't work, I'm going to have to put a bigger piece of equipment in. That is just not practical. You want to get your best shot of putting the right piece of equipment on that site, so when you do your testing, you get a reasonable result. So the advantages of field data, it does reflect the actual operational conditions. Disadvantages, it's highly variable. You don't own the site generally. You don't have 100% control of the site. Of course, it's weather dependent. That's the whole point of it. It is expensive and time consuming. And it is kind of site specific. You can move a piece of equipment from one site to another. They can be side by side and get two completely different results, even though they may be the same size. From our own experience, we've been working out in Washington with our upflow filter, trying to get that approved and through testing. And it's taken us about 5 years so far because of so many uncontrolled variables that we go beyond our control. And you'll be starting a site, you do your pre-testing, everything looks good, and you install your equipment, and things change, and you have to start again. And it takes you a year to precondition or pre-monitor a site, so you're back a year. So it only takes a couple of small things to go wrong, and site testing can be, suddenly you sort of got a lifetime job. And what you end up with your field data or field testing, you don't control the storms. So you number out your storms, you get some that are qualified and some that don't qualify for various reasons, but you just generate a whole lot of data, flow data, volume data, just literally bucket loads of data. And you boil it down a little bit, and you might be just interested in total suspended solids. And you end up with a chart, something like this, which has your inlet event mean concentration, your outlet event mean concentration, and a removal efficiency. And you get a whole lot of these numbers for all your storms, and you can plot that on a chart. And what you notice is this chart is not a nice little flow removal chart. You end up with a chart that goes, okay, storm 1, I got 78%, storm 2, I got 85%, storm 3, I got 53%. So you end up with an average, and hopefully that average puts you at your qualifying level of performance above 80% or whatever it might be. But your standard deviation shows that some of these storms and the results fall well outside the norm. Hopefully the most fall inside, and you sort of go, okay, how do I use this? This is all stuff that you spend a lot of time staring at going, what's it mean? What happened down here? What changed on site? Why were these ones poor? Why were these ones so good? So you try and develop all that. So field studies really are sort of a validation of sizing, because you need your lab data to initially size the equipment and get some sort of assumption of how big it should be for that site. One of the developments we've seen recently is outdoor labs. Because of all the variability of sites and the difficulty in getting one site to work and another vendor coming along and using a different site, outdoor labs are becoming more common. Using real runoff, they allow good characterization of the site, and they help accelerate the field testing. When you're dealing with lab data, you generally know what you're putting into the system and what's coming out. When you're dealing with field data, you kind of need more measurement. You need to measure particle size distributions. You should also measure particle density distribution, because unless you know all this information, you can't really assess what's going on in the equipment. Now, the last segment is empirical modeling. This is where, in most cases, you take one piece of equipment and you measure lots of times from one site or from one test. So you get lots of data points that all relate to one site. With the another way of doing this, and we do this with our industrial stormwater, is that we send out test kits to many sites. So we measure lots of sites and we bring the data in, and you build through multi-regressional analysis some sort of three-dimensional mathematical model that allows you to predict the performance of your equipment to remove one pollutant based on its association with another pollutant. So you can use something like TSS and measure that coming in, and then from that you can associate the removal of copper or zinc or particulate phosphorus as part of that. And we've found to some extent this is quite successful, and we're continuing to develop this model for our industrial stormwater. So another part of developing tools is that you test one size unit. And most vendors will test a 4-foot diameter manhole. It's usually the smallest unit that they manufacture, or they might make a 3, but commonly we use a 4-foot manhole. It fits in a lab, and you can have sufficient pumping capacity to test it to its maximum ability. So you've got to get from that 4-foot manhole to the 6-foot manhole, to the 8-foot manhole, to the 10-foot manhole. And the way you do that is through scaling. And most current test protocols have a method of scaling built into them. The most common, and this is becoming very common now, is what we call surface area scaling, where you just keep the load rate constant. So if I test my 4-foot unit at 35 gallons per minute per square foot, I then assume that my 6-foot unit is going to perform the same at 35 gallons per square foot. So I can increase the flow rate by the increase in square foot. It's the same way we scale ponds. It's the same way we scale any surface area type system, and that's most commonly used now. So most tools will use that. There are some regulators out there that have allowed quasi sort of 3-dimensional scaling, where depth comes into it, and you end up, instead of using a factor of 2 for your scaling, you might be using 2.25 or 2.5, because it's not strictly a linear scaling. They allow a non-linear scaling. So sizing methods. If you were to go to a vendor and ask them to size a piece of equipment for you, they can do it one of 2 ways generally. One is the single storm event sizing, where you just take one design storm, which might represent 90% of all storms or less than that, and just size for that one storm. Or you can do this long-term runoff or net annual historic rainfall sizing, where you run through the system the historic rainfall data from the nearest rainfall station. Most vendors have this software built into their design toolkit now. So if we look at the single event sizing and what it actually does, it's just that. We take, say, the rational method or TR20 or TR55, and you put the area in, and you work out what your peak runoff is for your design storm. In this case, it might be 1.13 CFS for this 0.85 acres. Now, if you remember the slide from Caltrans showing the pollutant runoff in those little jars, they're on the front side of that hydrograph. So coming up this side, that's where the pollutant should be, hopefully. It's in this side. So if I size my piece of equipment to treat this flow rate, it should be conservatively sized so that it's removing more than, say, if I size for 80% here, it should be removing more than 80% at these lower flow rates. So that's where the equipment's designed to perform, at that peak flow rate. So that's a single event. And then I can just take that flow rate, go into my sizing tables or my sizing charts and say, okay, if I need 1.13 CFS for 80% removal, probably need a 4-foot diameter unit. It might be different if it's a predefined or pre-approved system through a regulator. You might be a slightly different size based on their flow rates and their requirements, but you don't generally need software. That's a fairly simple way of sizing. It's conservative. It's not too bad. With the net annual sizing, this is kind of where you need a spreadsheet, the vendor software to do this, because you do quite a number of calculations. If we look at a long-term rainfall record and we put intensity along the bottom here and the chance, the percentage of storms exceeding that intensity or less than. So if we look at this, say 0.2 inches per hour, 48% of the storms are less than that intensity. So we can take all this rainfall record, all these different intensities and their percentages, and we can boil it down to, when we look at the rainfall station, a table. So to do a net annual calculation, and net annual calculations are written into quite a number of stormwater manuals. So this is not an uncommon sizing. This is quite a common sizing method. I can take my 0.02 inches per hour, and I can work out that it's 6% of the total rainfall record. And I can just keep doing that for different intensity bands. At 0.04, that's responsible for another 6% of the total rainfall. So I end up with this table. And somewhere around about, we see here about 1/2 inch per hour, or a little over, getting close to 1 inch per hour. We start to run out of rainfall. We've actually accounted for almost 100% of the total rainfall coming down in that record. So we break it up into this. Now we can take this table and put it into our sizing tool and just use the rational method now. So we have our intensity for our site, and it doesn't really matter what it is. I can use the rational method and calculate a flow rate. So now I've got a flow rate. I can take that flow rate and go to my charts for my piece of equipment and work out that at that flow rate I can remove 94% TSS. But that's only 6% of the total rainfall record, so I'm going to factor that in. I'm going to multiply my 94% removal by my 6% of the rainfall record and get a weighted removal efficiency for that intensity of only 5.5%, which is fine. I do that for every intensity band and sum it all up at the bottom, and I get this weighted removal efficiency of 94%. So let's see how this affects a site. If I take a 3-acre site, 85% impervious, and I look at the 1/2 inch runoff depth, and I throw that into HydroCAD with TR20 and with a little bit of reiterative processing, I can work out that that storm on that site is going to produce a peak runoff of 2.76 CFS. So I can go down and say 2.76. I'm probably going to need a 6-foot unit, and I'll install a 6-foot downstream defender. I'm good to go. Now, if I turn around and go, what if I do a net annual sizing on that? How would that change things? If we look at doing the table, we do our software, and we do the net annual sizing, what we see here is that the rainfall record is really heavily weighted so that the small intensity storms, which are the most common, really account for a high percentage of the removal or of the total flow. So by the time I get to about 0.06 inches per hour in this site, I've got about 81% removal. So my software is going to say, you can use a 4-foot unit, or you could use a 6-foot or an 8-foot. They're all going to remove about the same, because on a net annual basis, these small storms really have a big influence on the sizing, because that's where the majority of the rainfall volume is. So what are the difference? The net annual sizing is going to give you a smaller unit because of the influence of the frequency of small intensity storms. Now, because of that, there may be some risk of early bypass, especially when you consider maybe a site that may be sloped with some grade to it, so you have a very short time of concentration, and you might have a fairly high runoff rate relative to the intensity. So there is a risk of an early bypass in some of this, and the rainfall distribution is highly influential on the sizing. And at this point, we also notice that there's quite a bit of variation in rainfall distribution analysis. So between vendors, the rainfall distribution analysis for the same station could be significantly different. With the single event sizing, it's more conservative. It will result in a larger unit. It may increase the cost, but it's generally more robust. So in terms of a water quality outcome, if it's not specified, you might size on a net annual basis or on a single event basis, depending on the sensitivity of the site. You might consider the receiving waters, the size of the site. Smaller sites, it's not really going to matter much between them, because when you come down to the small end of the scale, it's still 4 foot for 4 foot. It's going to come in more when you get to the larger site. You start looking at 3, 4, 5, or 10 acres, and you end up with quite a difference in sizing when you're net annual sizing on a larger site as opposed to single event sizing on a larger site. So validation, this is an important part of it as well. And if you happen to be an insomniac and you love reading technical reports, there are some great places for you to go. 2 of them is the njcat.org and their database, which has a lot of really good reports that are submitted for NJDEP approval. And there's just a bunch of stuff here you can download and read and look at the data behind equipment and how it's been tested and what the results were. And also the BMP database.org is another resource. It does require a lot more looking to work out exactly what it is that you're looking for. Now, certification is really important as well. As I said before, bad data, uncertified data is not necessarily bad data. But if you're talking to a vendor and they're sending you data or they're doing sizing, don't hesitate to ask questions about the origin of that data or the origin of that sizing, to be comfortable with the sizing, especially if you're looking at large sites and small pieces of equipment and you look at it and it just doesn't feel right. You want to say, well, how did you get this? Did you use what data? Can you give it to me or show me the theory behind this? Because sometimes we just see some odd sizing. We go, just practically speaking, the equipment's too small for the site. So, one way of doing it is using a pre-approval performance, such as New Jersey DEP or Washington DOE, or the city of Indianapolis. There's a lot you can look at in there. Now, I'm just going to touch on this a little bit because this comes up quite a bit. When we look at Washington DOE and New Jersey DEP at the moment, you're going to find that they certify for something like 50% removal for a separator. And many stormwater manuals reference them require 80% removal for a separator. And it's a little bit of a disconnect now. There have been recent updates to New Jersey and Washington, and basically they're looking around about 50% for a separator. So how do we work out whether to get to 80%, whether the piece of equipment can get to 80%? Well, if I look at this record, if I was in New Jersey And they have a particle size distribution which runs from about 1,000 microns down to about 2 microns. Overall, of that distribution, when I do my testing, at this flow rate, I get 46% removal. And you say, that's not enough. I need more. But the bottom line is, when I'm testing a separator, I find that the performance was really good down to about 50 microns. And if I look at that particle size range down to 50 microns, the D50 is around about 136 microns, and I get about 94%, which is a really good result. So you need to understand what's behind this testing protocols, the particle size distribution, because when you look at a separator, this stuff below about 50 microns, it's filtration material. You're not going to get it with a separator anyway. So to include it as part of the test is kind of like it's asking it to do something it was never designed to do, and it falsely limits the equipment by saying, well, you didn't get this, so you only get that score. Well, you're never going to get that. And really, the application of the equipment, this equipment, if you're using a separator that's designed to get down to about 50 micron or does down to about 50 micron, shouldn't be used on a site where you're looking at 20 micron or less. So it's a horses for courses type thing. So in stormwater manuals, and this is, as I say, many stormwater manuals have been updated in recent years, and also New Jersey and Washington DOE have been updated in recent years. And what I'm finding is there is some disconnect between references and manuals requiring 80% TSS, but then referencing New Jersey or Washington, where they are only certified for, say, 50%. The intent may be to use a separator, but the influence, the net result is that if you want 80% removal using those certifying agencies, you end up with filters. I think that sort of, it's got to be worked through over the next few years as people update their stormwater manuals. Remember, vendors can help. We're a resource. Use us. Give us a call. It's important that we talk and have a dialogue and you understand how we're sizing a piece of equipment for you, or when you size something or you get one sizing from one vendor and you get a different sizing for a different vendor, usually the answer is in the sizing methodology, whether it was net annual or it was done on a single event. Now we have a website here, hydrointernational.com, BMP sizing. I don't think there's a direct menu option for that. If you just type that into your web browser or download the PDF and click on that link, that'll take you to a page where you can get access to most of our tools. And if there is something you need specific to your needs, that's what we're here to do, so don't hesitate to call us. So with that, I think I've got to the end of the presentation. I think it is a fair bit to go through. I touched on it fairly lightly. To go any deeper would be to put you to sleep, I think. So I want to thank you for your attendance. As I say, the PDHs will come out tomorrow. There will be a follow-up survey. And I really appreciate everyone coming online and listening to this presentation. So thank you very much. My email is ptaylor@hydro-int.com. If you have any questions, feel free to email them to me and I will answer them straight away. Thank you very much.